petrol fossil fuel energy system is a scam. As anybody that understands how the universe works knows that electric flows freely through the atmosphere. You also notice how they enjoy blaming the humans. You know, yeah, we do a lot of stupid things, but the ones that are controlling the situation guide humans to do the wrong thing. If we were given right information, we would make the right decision. One thing I have to say about the Kilauea situation is that these people were fracking on a volcano and drilling into it to create geothermal energy. Do you think that sounds smart? I don't.
Good evening. Oh, good, I get response. That's great. Welcome to the USGS Evening Public Lecture for May. And we're just sneaking this in the last day of the month. Mitch, is it on? Okay, they told me to hold it closer. Thank you. Due to some unforeseen circumstances, we will not be having a June lecture, but the good news is we will resume and have a July lecture on July 26th, and it's going to be on acid mine drainage. So I'm really encouraging you all to pick up the flyer in the back. I'm trying to fumble with this, so that you can remember July 26th for that lecture. But what you're really here for tonight is our lecture, Yes, Humans Really Are Causing Earthquakes, How Energy Industry Practices Are Causing Earthquakes in America's Heartland. And it's presented by Justin Rubenstein. Dr. Justin Rubenstein is a seismologist and Deputy Chief of the Induced Seismicity Project here at USGS in Menlo Park. His research focuses on the ongoing surge of seismicity in the central United States and its relationship to oil and gas operations. This work includes developing methods to estimate the likelihood of earthquakes induced by oil and gas operations and field studies of seismicity in Colorado, Kansas, and Oklahoma. Dr. Rubenstein has worked on many topics related to earthquakes, including earthquakes forecasting, controls on earthquake ground shaking, and causes of damage in the 1994 Northridge earthquake near Los Angeles. Justin received his bachelor's degree from UCLA and his master's and doctorate from Stanford University. So without further ado, let's give a warm welcome to Justin.
Thanks, Diane. So as you can see from the title of this presentation, I'm pretty definitive about whether these earthquakes are man-made. We are causing these earthquakes. And what you can see here is just a picture of a pump jack on the left-hand side, an annual count of earthquakes in the central United States by year. You can see that from 1990 through 2008 or so, the earthquake rate was more or less constant, somewhere around 20 magnitude 3 earthquakes per year. And something dramatically started changing in 2009, such that we had a spike of over 1,000 magnitude 3s in 2015. Fortunately, it has begun to decline in the last couple of years. And most of these earthquakes are actually in Oklahoma. I think most of us think of tornadoes when we think of Oklahoma. But I just found this Photoshop of a Welcome to Oklahoma sign, and it's the home of not just tornadoes, but also earthquakes. So the Quake-nado is there. So yes, humans are causing earthquakes, but it's not in the way that you think. It's not Max Zorin trying to put nuclear bombs in the San Andreas Fault, nor do we have James Bond to save us in A View to a Kill. Similarly, it is not Lex Luthor trying to flood the San Andreas Fault in Superman 1. And again, we do not have Superman to save us either. Remarkably, though, the way that Lex Luthor is trying to cause these earthquakes in this moving in 1979 is actually the way these earthquakes are being caused, by injecting fluids deep underground and into faults. So I apologize, we don't have any superheroes to protect you from these earthquakes. You're just left with scientists and regulators. So what we'll do over the course of this talk is I first want to give you a little bit of a history on induced seismicity, these man-made earthquakes. And it's actually much longer than you probably think. Then we'll go into how these earthquakes are actually physically caused and the oil and gas processes that cause them. And we'll go through a couple of case studies and sort of broader studies of induced seismicity, some of the more recent work. And finally, we'll wrap up and start thinking about where do we go from here? What is the outlook? Yes, the earthquake rate is going down, but is this something really permanent? So as I mentioned, induced earthquakes have been occurring for over 100 years. Now, just a brief stop for terminology. When I say induced, I mean an earthquake that is caused by human activity. It's an earthquake that probably would not have occurred if we weren't doing something. I may also use the word triggered. I use these words interchangeably. I use them to mean the same thing, earthquakes that were caused by human activity. So the first known induced earthquakes occurred in 1894, and they were felt in Johannesburg. Johannesburg at the time was a very small city. It was a gold mining city, and they were actually mining gold directly underneath town. And so they were mining in what's called room and pillar style mining, and it's exactly what it sounds like. You carve out a room and leave just small pillars. Think of what a parking structure might look like now. And so what was happening is you would start seeing collapses of these, and you would start feeling the shaking at the surface. And so that's what these first human-induced earthquakes were. And mining-induced earthquakes started to be felt in other locations, and this led to the founding of a seismological laboratory in Bochum, Germany, all the way back in 1908. And it also led to the founding of a seismic monitoring network in the Silesia coal basin in Poland a dozen years later, with the express purpose of studying these earthquakes caused by mining. And so there's a very long and rich history of mining-induced earthquakes and induced earthquakes in general. So the next historical example I want to bring up is from this garden spot in Goose Creek, Texas. So this is a photo from the 1920s, and what you see is oil derricks just everywhere. And so Goose Creek is on the coast, about an hour away from Houston, and so this massive production, so the extraction of oil is just going crazy there. And so this started causing earthquakes, the largest about a magnitude 4. And to my knowledge, these are the only earthquakes to ever have been felt in the city of Houston. So the last historical example of induced earthquakes I wanted to bring up is Lake Mead. So this is a recent photo of Lake Mead. Lake level is low. But when they started filling Lake Mead in the early 1930s, you're adding a whole lot of weight into this reservoir. And so the weight of this water actually started causing earthquakes in the area. Fortunately, they were relatively small, low magnitude 3 earthquakes, and these have more or less waned away. So we've now seen that induced earthquakes have been occurring for over 100 years, and we've also seen 3 different kinds of induced earthquakes. So what are some characteristics of induced earthquakes? When I see earthquakes occurring in a peculiar place where I don't think of natural earthquakes occurring, the things I start thinking about are these earthquakes close to some human activity that could be causing them? Are they close to a mine? Are they close to a reservoir? The second thing I start thinking about is, are these close in time? Was there some change in the human activities that could be linked to the earthquakes? And finally, are these earthquakes close to the surface? In general, human activities are at the surface or very close to the surface, so the effects of these activities are going to be close to the surface. And so these are sort of criteria that I start thinking about when I start thinking about whether or not an earthquake is induced. Unfortunately, these are not hard and fast rules. There are plenty of examples of induced earthquake sequences that violate one of these rules, and I can actually provide an example that violates all 3 of these criteria. So they're good things to think about, but they aren't something that you can directly rely upon. So why is it that induced earthquakes are suddenly an issue? We've known about these for over 100 years. And what's really happened is this dramatic increase in seismicity that I showed you a little bit earlier in the talk, is that the earthquake rate has increased by more than a factor of 10. You look at this period from 1973 to 2008, and we had 852 earthquakes, about 24 or so earthquakes per year. And in the subsequent 9 years, we saw nearly 3 times as many earthquakes in this much shorter period of time. So there's a very dramatic change. And again, I'm looking at magnitude 3 and larger earthquakes. And the reason we're looking at 3 and larger earthquakes is that we're certain that we're seeing all of these earthquakes throughout this study period. while our recording capabilities and our earthquake detection capabilities have changed over time and in general gotten better, even back in 1973, we were able to see all of these magnitude 3 earthquakes. So the signal that we're seeing here is not a function of our capabilities, but is actually a real signal. So let's take a look at what the seismicity looks like. So now we're looking at the period of time when there really wasn't a lot of induced seismicity. And you can see that seismicity is sort of scattered around the central United States. You can see that there's this structure of seismicity right here. This is the New Madrid seismic zone. This is an area of known natural seismicity. And you also can see right here the eastern Tennessee shear zone. This, again, is natural seismicity. But in general, the seismicity is sort of scattered around everywhere. You see some small clusters, but in general, it's sort of spread around somewhat randomly. And the average rate of earthquakes was about 24 earthquakes per year, again, magnitude 3 and larger. So then, if we look at 2009 through January of this year, we have 3,200 of these earthquakes. And if you go back and forth between these, I would guess that this figure has more earthquakes on it if I compare these. But actually, we just have so many earthquakes lying on top of each other here in Oklahoma, it actually just looks like there are less earthquakes. And so our earthquake rate over this span of 9 years is now 357 earthquakes. But if you recall, we had a year with over 1,000 earthquakes per year. So this is really actually lowered by some of the lower rate earthquake years. And so this earthquake rate increase is limited to just a few areas. So now if we look at what we're looking at here now is a cumulative count of earthquakes. And so if we expect that earthquakes are going to be happening on a random basis at more or less the same earthquake rate, we'd expect there to be a line. And that's what we see right here from 1995 to 2008. And things start turning upward because our earthquake rate is increasing. So what I want to do is really show you that the increase in the earthquake rate is just coming from a few places. Now, I've alluded to the fact that Oklahoma and southern Kansas is really the source of most of this earthquake rate increase. So let's just subtract out the earthquakes from Oklahoma and Kansas and see what happens. Well, we've almost flattened out this line completely by just subtracting out Oklahoma and Kansas. And we know these earthquakes are induced. But let's subtract out some other induced earthquakes. We can subtract out the Raton Basin here in southern Colorado, northern New Mexico. We can subtract out the Guy-Greenbrier sequence in central Arkansas. We're flattening out even further. And if we take out a few spots in Texas, we've now flattened out completely. So now we're looking at a linear accumulation of seismicity. So what we're seeing is that the natural seismicity rate really hasn't changed. We're just seeing a change in seismicity in a few areas, and these are all areas where we're seeing induced earthquakes. Now, the earthquake rate increase that we're seeing in Oklahoma is so dramatic, the earthquake rate in Oklahoma is now higher than it is here in California. And so what we're looking at here, again, is a count of magnitude 3 and larger earthquakes. Shown in blue is California, shown in red is Oklahoma. California's earthquake rate is sort of rattling around somewhere between 3 and 500 magnitude 3s per year, with the exception of these 4 spikes. These 4 spikes correspond to the timing of large earthquakes in California. As you would expect with these large earthquakes, you're going to have aftershock sequences, so you're going to have a very high earthquake rate. But you can see it drops back down the year after all of these earthquakes. Oklahoma, on the other hand, is averaging about 1 or 2 earthquakes a year until 2008 when it starts creeping up. And then in 2014, it surpassed California. And for the last 4 years, it's been higher than the earthquake rate in California. And right now, the projection is for 2018, we expect the earthquake rate to be very similar in both California and Oklahoma. Now, I've been talking about magnitude 3s for a while now. It's not just magnitude 3s, and it's actually, we're starting to see significant damaging earthquakes. And so these are 2 photos from earthquakes in 2011 that happened just a couple of months apart that really brought people's attention to this problem. These were the first really significant damaging earthquakes that we've seen in this surge of seismicity. The picture on the left is from an earthquake in Trinidad, Colorado. This is the Raton Basin, so southern Colorado. You can see that this is sort of an old storage facility with a brick facade, and it lost a lot of its facade. And here's a photo from the Prague, Oklahoma earthquake, and you can see again this is a home that lost its entire brick facade. So we're starting to see larger earthquakes. And even though the earthquake rate started to decline in 2016, we started to continue to see large earthquakes. And in fact, 3 of the 4 largest earthquakes to occur in Oklahoma happened in 2016. The first happened just a few weeks into 2016. We had the magnitude 5.1 Fairview earthquake. You can see some small amount of damage associated with that earthquake. Then the magnitude 5.8 Pawnee earthquake was and is the largest injection-induced earthquake that we've ever observed. And then a few months later, we observed the magnitude 5.0 Cushing earthquake. And this earthquake was actually the most damaging of all of the earthquakes that we've seen in Oklahoma, despite the fact it is much smaller than the Pawnee earthquake. And the reason is that this Cushing earthquake more or less occurred in town, where these other earthquakes were really occurring in very rural areas, so we weren't seeing a lot of damage. And so this is really something to sort of step back and think about, that we've been very fortunate that most of these earthquakes are occurring in rather rural places. And in fact, the city of Cushing is relatively small. It's somewhere around 3,000 or 5,000 people. We're not seeing earthquakes in Oklahoma City. We're not seeing earthquakes in Tulsa. Now, Cushing is also very important because it's a location of very critical infrastructure in the United States. Cushing calls itself the pipeline crossroads of the world. There are 9 major pipelines that cross through there, including, many of you probably know, the Keystone Pipeline and the hotly debated Keystone XL pipeline go through Cushing, Oklahoma. And because it's the pipeline crossroads of the world, there's a whole lot of oil and gas storage. Approximately 10% of the U.S. crude oil is stored in this one town. Now, these storage tanks I've been out to visit. They're about a football field across. They're gigantic. And if you take a look at this Google Earth image, you can see that there are a whole lot of these. They're really everywhere. And so in the city of Cushing, they can store about 60 million barrels of oil. For the beer drinkers in the room, that is 2 kegs of beer. If you're not a beer drinker, think 42 gallons. So your fridge is going to be awful full with the milk. So Cushing, as you can see, is a very important place, and it has experienced a lot of earthquakes. We were fortunate last year not to see any magnitude 4s in the area, but as I mentioned, there was a magnitude 5 in 2016 and a few magnitude 4s in 2014 and 2015 as well. So the next thing I want to show you is an animation of the seismicity in Oklahoma. I've shown you in a graph how these earthquakes have behaved, but I feel like this animation really shows it better. You'll see things popping up. Those are going to be earthquakes, but you'll also start hearing the earthquakes. So the seismicity is going to sort of start in this area in here. This is near Oklahoma City. We'll see the Prague earthquake happen here, and then we'll start to see seismicity move northward through the Hutton Formation and then Mississippi and into Kansas. So I'll just let you listen. I really can't put it any better than that. It's an incredible earthquake sequence that we're seeing there. It ends in 2016, so really sort of at the peak of the seismicity, so we don't actually hear the decline, but you can see what a dramatic change that we've seen there. Now, you may be saying to me, Justin, you have all these earthquakes, but Oklahoma didn't have earthquakes in the past. How is it that they're having earthquakes? There's no faults there. Well, actually, there are a whole lot of faults in Oklahoma. So what we're looking at is a map of faults in Oklahoma that was produced by the Oklahoma Geological Survey, and they worked in collaboration with industry, with a whole lot of industry collaborators to put this map together. If you looked at this map from 10 years ago where they didn't have industry input, there probably would have been 10 lines on here. But industry was very generous and shared a lot of their geologic knowledge of the area so that the OGS could get a better handle on what is happening in the area. And so now that you see that there are faults everywhere, it makes more sense that you can have earthquakes just about anywhere in Oklahoma. And this is really the case just about anywhere in the world. There are going to be faults just about everywhere. They may not be active, but there are faults there. So let's now walk through the different oil and gas operations that can be causing these earthquakes. Many of you are probably thinking hydraulic fracturing is the source of most of these earthquakes. Well, that's not the case. We'll walk through that why that's not the case. But this is just a photo of a frac site. The largest earthquake we've seen associated with frac jobs is about a magnitude 4.8. Oil production has actually been linked to very large earthquakes, earthquakes as large as about magnitude 7. There was a series of 3 magnitude 7 or so earthquakes that occurred in the late 1970s and early 1980s in Uzbekistan. Unfortunately, we don't know a lot about what was happening there because there wasn't a lot of communication between the USSR and the West at this time. The other 2 ways earthquakes are going to be induced is a process known as wastewater disposal. This is our real bugaboo. This is what's causing the earthquakes we're seeing in Oklahoma, and the largest earthquake that we've seen associated with it is a magnitude 5.8, the earthquake that occurred in Pawnee in 2016. An enhanced oil recovery, another injection technique, has caused earthquakes as large as magnitude 4.5. So how is it that these 4 different processes cause earthquakes? 3 are injection and 1 is extraction. So these are the 2 different ways that earthquakes can be caused. And I'll really focus on this one here, and we'll go through an animation to look at this second one. So more or less, as I said, we're either putting something in or taking something out of the earth. And so we're adding mass or reducing mass in the earth. And so we're going to be pressing down even harder on faults or relieving stress on these faults. And so this can encourage or discourage faults. And I think a few years ago, a lot of us were really discounting this mechanism as being particularly important. But a number of modeling studies that have come out in just the last couple of years are showing that this is turning out to be a more and more important mechanism for these earthquakes. But we still think this is probably the primary mechanism for most of these earthquakes. And this is related to fluid pressure. So how is it that injection causes earthquakes? So what we're looking at right now, here's an injection well that's drilled down into our injection formation. So we'll start injecting fluid, and the water's going to go down this well into our injection formation. You can see right now this fault is being clamped closed by the regional stress. Fluid is going to be flowing outwards into this formation, and eventually this fluid is going to penetrate our fault. And while it penetrates the fault, it's going to be prying that fault open. And so releasing some of the stress that's holding it closed, making it more likely to slip in an earthquake. You might want to imagine it somewhat like an air hockey table. When the air hockey table is off, your puck isn't going to slide very quickly. But as you turn the air on, the puck slides very smoothly. And that's more or less what we're actually seeing here, is as you fill up the fault, you're starting to turn on the air in this fault, make it easier for this fault to actually slip in an earthquake. So now let's walk through hydraulic fracturing and wastewater disposal. These are the 2 ones that we really think about a lot. So up here is a photo from a frac site, and you can see it's an incredibly complex operation. It's amazing the amount of technology that's going on in these. This is a photo from a frac site I visited a number of years ago in Weld County, Colorado, and these are water tanker trucks. There's about 100 of these waiting to inject their water underground just into one well. And so these are use an incredible amount of water to frack an individual well. So it's a massive operation. So hydraulic fracturing is actually a very old process. It was invented over 70 years ago in the Hugoton field, and in some sense it is intentionally making earthquakes. You're trying to make earthquakes that are very small, somewhere on the order of a magnitude -2 to a magnitude 1. An earthquake that you and I are never going to feel at the surface. And it really is a high pressure injection intended to increase your permeability. If you look at this cartoon here, if you think of a well that before it's been fracked, you might only be able to access sort of these shaded areas of oil. And the idea is after you've fracked the well, you're able to access a much larger area. Now, a frack job is going to be typically short duration. It's going to last hours. An entire well might take a few days to frack. So it's a short duration operation. And the amount of water that's going in, it sounds like a lot, but in the grand scheme of things it isn't, is about 100,000 barrels per well. And after you frack your well goes into production. You extract out your frack fluid and you start sucking out the oil, because that's why you fracked this well in the first place. So we can look through an animation here to show you what hydraulic fracturing is. So here we've started to drill our well, and this is going to be our pay formation right here. And so you've turned the well to stay in this pay formation because you want to extract as much resource as you can. So if you can access oil across the length of this well, you're going to be able to get much more. So right now the well is bare. There isn't anything holding it closed. So they pour cement down it. And they pour the cement down it so that it has structural integrity, so that it's not going to just collapse in on itself due to the weight of the earth around it. But now we're sealed off. And so what they need to do next is actually create perforations so that you're able to get the oil to flow in and out. And so they've lowered a gun and set off charges and perforated this well. And so you can see the holes here, here, here. And so they pull out the gun and then start to inject water, again, at very, very high pressures. And so the water will flow down the well, hopefully any second, and it'll go out of these perforations. And as you raise this fluid pressure higher and higher, it'll eventually exceed the strength of the rock and create these fractures. And so now you're able to access oil that's in a much larger region. And so this is just one frac stage. And in a long well like this, you'll frac multiple stages. And so the next thing we'll see is that this area right here will be perforated and then fracked, so that they're able to access the oil in this area as well. So, as I mentioned, wastewater disposal is the other major source of these earthquakes. Actually, it is the major source of these earthquakes. Hydraulic fracturing really is only responsible for a very small percentage of the earthquakes. But first, we have to ask the question, what is wastewater? And wastewater, especially in Oklahoma, is primarily what is known as co-produced water. Now, oil and gas are the decomposed biological components of relict oceans. And so what this means is trapped in the same space as the oil and gas is the salt water that's left over from these oceans, and now it's even saltier. And so when you pull out oil and gas, you're going to be pulling out salt water. It's not really a choice. And this is just a simple schematic. Here you can see this is a reservoir rock here, and you can see the oil is floating on top of salt water. And so when you pull out oil, you're going to get salt water with it. It's not a choice. And in parts of Oklahoma, you're looking at very, very resource-poor reservoirs. You're looking at 20 parts salt water to 1 part oil. So you've got a lot of water that you've got to get rid of. And so this is the major component of wastewater in Oklahoma. In other parts of the country, it's actually spent frac fluid. It's water that you've put down to break up the rock. But in general, operators want to reuse frac fluids because frac fluid is primarily fresh water, and fresh water is not cheap. So your options to deal with all of this wastewater is, well, first, if you can reuse it, that's obviously going to be your best option. The next option is, well, surface discharge. Can you clean this water up enough such that you can use it for agriculture or put it into a river or something like that? But what is very commonly done is you dispose of this water at depth into a wastewater disposal well. And so a wastewater disposal well, you're going to be injecting into a very porous formation, something that'll take this water easily. And you're going to operate this well probably for years or maybe even decades. Some of the largest wells you can inject over 1 million barrels a month, so much bigger than a frac job. And over the course of history in the United States over the last few decades, there have been about 35,000 of these operating in the U.S. I believe there's about 30,000 that are active at the moment. And not actually too many have been connected to earthquakes. So this is what a wastewater disposal well looks like. You're injecting down into this porous formation here. Hopefully the water goes into this formation and you never hear from it again. And, well, that's generally what happens, but not always. So let's now think about what we just learned about wastewater disposal and hydraulic fracturing and figure out which is more likely to cause earthquakes. Wastewater disposal is a long-term process. You're operating for years or even decades, and you're injecting high volume. Some of these wells, you're injecting over 1 million barrels a month. Fracking, you're injecting over a few hours or a few days, and you're injecting, relatively speaking, a much smaller volume. And so fracking is going to be affecting a much smaller area over a much shorter period of time. And so we would expect that wastewater disposal to be more likely to induce earthquakes. And well, that's exactly what we see. Wastewater disposal has been associated with many felt earthquakes and many damaging earthquakes, the largest of which was a magnitude 5.8. Hydraulic fracturing really has been linked to very few felt earthquakes. And to my knowledge, there hasn't been any damage associated with frac-induced earthquakes. And the largest frac-induced earthquake is significantly smaller, a magnitude 4.8. And in fact, for some reason, all the largest frac-induced earthquakes that we're seeing are being experienced in Alberta and British Columbia as opposed to anything here in the United States. And again, this is despite the fact there are many, many more frac stages that have been completed than there are wastewater disposal wells. So now I've told you that hydraulic fracturing isn't a new technology. I've told you wastewater disposal isn't a new technology. So why is it that we're suddenly seeing all of these earthquakes? And what has changed is a change in drilling technology. Now, traditionally, wells were drilled vertically. And so again, if this is your reservoir formation, this is where you're going to be extracting your oil and gas. And so you're going to be producing some amount of produced water. Let's imagine it's a kiddie pool. But what has been developed in the last 15 years or so is they're able to steer the wells and steer within a narrow formation. And what that means is that they're able to produce formations that have much lower ratios of oil to water. So you're able to produce areas where there's just going to be more salt water coming out. And the average horizontal well produces 10 times more water than these vertically drilled wells. And so this is the source of these earthquakes. We're producing way more water, and this water needs to be injected. And so it's this dramatic increase in fluid that's generated from the horizontally drilled wells that's the source of this. So let's walk through a couple of historical examples, and we'll first look at how we discovered that fluid injection can cause earthquakes. So this goes back to the early 1960s to the Rocky Mountain Arsenal. Rocky Mountain Arsenal is just outside the Denver area, and at the time they were producing chemical weapons there. As you might guess, chemical weapons have a lot of nasty byproducts, and you need to get rid of them one way or another. And so the Army drilled a deep well and started injecting away. Injection peaked at about 130,000 barrels a month. And shortly after they started injecting, they started to see earthquakes. So here we can see just a count of the millions of gallons of fluid injected per month over the course of 1962 to 1965. And up here we're looking at the earthquake rate. And you can see earthquakes start up just a month or two after injection started. And the amount of earthquakes correlates reasonably well to the amount of fluid that's injected. They turned off injection for almost a year in 63 and 64, and you can see the earthquake rate dropped. Then they turned the well back on, and the earthquake rate went back up. And they abandoned the well in late 1965 because they realized what was actually occurring. A couple important things to take away from the Rocky Mountain Arsenal. First, the largest earthquake we saw associated with was a magnitude 4.9, and there was some damage associated with it. Here you can see damage to a bridge. But another important takeaway from this is this earthquake, this largest earthquake, happened over a year after they stopped injection. And so what this tells us is even if you stop injection, it doesn't mean that your hazard has gone away immediately. So this is not a magic bullet by stopping injection. The other important takeaway is in this figure right here. So here we're looking at a cross-section of the Earth. So we've taken a slice into the Earth, and so this is down. This is up and down. And so here's the surface, and here's the well, and this is the bottom of the well where you're injecting. And so now we're a year and a half after they stopped injecting. And so we've plotted all the earthquakes in the area, and you can see nearly all of the seismicity is 3 miles or more away from this well. And so this tells us that you can have earthquakes at very significant distances away from the source of the cause of these earthquakes. So the next historical study that I wanted to mention is work that was actually led here out of the USGS office in Menlo Park. Pictured here are Jack Healy and Barry Raleigh, and they worked with John Bredehoft, and they managed to convince Chevron to give them control of part of one of their fields in western Colorado, in Rangeley. And they wanted to test the hypothesis whether or not fluid pressure was important, where I showed you in that animation how these earthquakes are being caused. And they said, our hypothesis is if we inject, we're going to cause earthquakes. And then if we suck out all the water and return this area to its natural state, to its natural fluid pressure, we're not going to have earthquakes. And if this is true, this is going to prove that fluid pressure really is the cause of these earthquakes. And as it turned out, that's exactly what they saw. So here again in these two figures, we're looking at a cross-section into the earth. So these are the wells going down here. And so we're looking at a 6-month period here where they're injecting. And you can see that there's seismicity right at the bottom of these wells, and then there's some seismicity a few miles away. And then they said, all right, let's turn these wells off, let's suck everything back out, and return it to its natural state. So we've now gone from a 6-month period to a 1-year period here. And you can see there are almost no earthquakes. And so this really shows us that it is the fluid pressures that are causing these earthquakes. And this is really a remarkable study, and to my knowledge, there really has been no other case where we've really been able to actually sort of control earthquakes. So I next want to walk you through a modern study of induced seismicity. And the reason I showed this one is I feel like it was an incredibly thorough study to try to really make sure that these earthquakes were induced. And so in late 2013, people in the city of Azle, which is an exurb to the west of the Dallas-Fort Worth, started feeling earthquakes as large as mid-magnitude 3. And so the USGS, along with Southern Methodist University in Dallas, started studying these earthquakes. And so originally, these earthquakes are occurring in Texas. We don't have a lot of earthquakes there, so we don't have a lot of seismometers there. And if you don't have a lot of seismometers, you're not able to detect small earthquakes, and you're not able to locate those earthquakes well. And so this is what the distribution of earthquakes looked like, and it's about 20 miles across here. So you're not going to be able to figure out what well is causing these earthquakes if your distribution of earthquakes is 20 miles across. So we went in and put in some seismometers in the area, and we were able to reduce that cloud to now a 2-mile across. And so now we're really able to understand what is happening there. And so with this information, Matt Hornbach and colleagues, both here at the USGS and at SMU, really considered all the possible causes for these earthquakes. He asked the question, could these earthquakes be natural? Could these earthquakes be caused by lake level changes in Eagle Mountain Lake? This is a big reservoir right here. Could it be due to water table decline? Texas had been in a very prolonged drought at that time. Or could it be related to oil and gas production, some extraction of oil, or related to wastewater disposal? So they first considered whether or not lake level changes could be causing it. And here's just a plot showing you the lake level, and here's the time of the earthquakes. And you can see the lake level is at its lowest over this period of 6 years. But the stresses associated with this lake level drop are incredibly low. So here's a location of the earthquakes, and this is showing you the change in stress associated with this. And you can see that stress changes are only located immediately under this lake. And these stress changes are incredibly small. They're less than a kilopascal. We generally expect something to be triggering an earthquake. You need an absolute minimum of 10 kilopascals or more. And so we just don't think that this drop in the lake level could really have anything to do with these earthquakes. They also considered the water table decline, and the effects were even smaller than the lake level change. So they were able to rule these out pretty quickly. So the next question was, could it be oil production? And if you take a look at this Google Earth image, you can see that it looks like it's pockmarked everywhere. Well, those pockmarks are actually the location of oil wells. So there are oil wells just about everywhere here. And that's what this map is also showing. So each of these symbols represents an oil well, and the lines are showing you the direction that the well is going. So there are wells absolutely everywhere. So it's certainly possible that these are related to the earthquakes. And there's also 2 high-volume disposal wells that we see here and here. And so what Matt and his colleagues did is they computed the stresses associated with both the production of oil and gas and the injection of these earthquakes. And you can see that all the earthquakes are located right at the edge of the areas of highest pressures associated with the injection and extraction of these fluids. And not only that, they were able to show that the timing of these earthquakes corresponds very nicely with the highest stresses. So we can see right here, these are the plots of the stresses, and these stems here are showing you the timing of the earthquakes. And at the period of the peak, the earthquakes are occurring. So it's a very clear temporal and spatial correlation. So now I want to step away from a site-based study and start looking at some broader studies. So I'm going to be presenting some work done by Matt Weingarten, who at the time was a graduate student at Colorado University and is now a postdoc at Stanford. And he and I and a number of other scientists worked on this. And what he did is he gathered all of the injection well data for wells across the central United States. And so a real Herculean effort to gather all this data. There's 27,000 wells that he gathered data on. And if you look at the well density in the area, you can see that most of the wells are going to be concentrated in North Texas, Oklahoma, and parts of Kansas. And so Matt wanted to ask the question, are there certain injection behaviors that make it more likely to cause earthquakes? And so to answer that question, he said, all right, which wells could be associated with earthquakes? Which well is operational at the time that there's an earthquake within 10 miles? He sort of said that was a plausible sort of argument that well could be causing those earthquakes. And so shown in blue are wells that are not associated with earthquakes, and shown in yellow are wells that could be associated with earthquakes. That doesn't mean they're causing earthquakes, but they could be causing earthquakes. And so what he did is he said, all right, let's think about the parameters that seismologists really think are related to increasing the probability of causing earthquakes. And so injection rate and the total amount that you've injected were the first things that we sort of thought about. And so what he's done here is he's plotted the percent of wells associated with earthquakes, and we're plotting it against the maximum injection rate. So all the wells that injected 100 barrels a month were on average somewhere around 40% of the time associated with earthquakes, whereas wells injecting over 1 million barrels a month or more were about 80 or 90% of the time. But obviously we expect there's going to be some amount of random correlations. And so if this blue line lies within these red lines, which is what we would expect for sort of a random correlation, we don't think there's a real signal. But as you can see, once we get to about 200,000 or 300,000 barrels a month, we're well above these lines that indicate that we're probably seeing a random signal. And so what we can confidently take away from this is once you get to these very high injection rates, you're much more likely to be causing earthquakes. Looking at total volume here, you really don't see a very significant signal, which we found pretty surprising. We also didn't see any correlation with proximity to basement. Now, what I mean by basement is the really hard rock. In general, you're going to be injecting into sedimentary formations. Sedimentary formations really aren't strong enough to actually produce an earthquake. The stress doesn't build up enough to produce an earthquake. So you really need these strong granites to produce earthquakes, and these are going to be below the sedimentary section. So it stands to reason that if you're injecting into the basement or close to the basement, it's going to be easier for those fluid pressures to get to those depths. But we didn't see any connection in this study, nor did we see any connection to injection pressures. That's probably actually related to the quality of the data as opposed to whether that connection exists. And obviously, we're not going to be able to control for geologic factors. We're not going to be able to control, is there a fault nearby? We're not going to be able to control, is there a way for the fluids to get to depth? So we don't have all of the information. And so some work that Matt has done that is still in review, but I think is incredibly compelling, is they've looked now just at Oklahoma and Kansas, and so this is updated through last year, so there's about 4 more years of data. And so they were able to show not only is injection rate important, but total injected volume is important. And we think part of the reason is we've now had a number of more years, and you're going to expect your injection rate and your total volume to be correlated. Because if you're injecting at a high rate for a number of years, you're going to have a lot of total volume. But they were also able to show that proximity to basement is important, so being close to these hard rocks. So now we're looking at proximity to basement. So 0 is going to be you're injecting into basement, and this is the percent of the wells that are associated. So you can see the red line is showing the percent associated, the black lines are showing random. And so you can see until you get to about half a kilometer, so 2,000 feet or so away from the basement, you're more or less looking at a random association. But as you get closer and closer to the basement, or actually into the basement, the probability that you're going to be associated with earthquakes dramatically rises. And so we can take away from this that the proximity to the basement is very important. Still no evidence of injection pressure, and obviously, again, they can't control for geologic factors. So now I've walked you through a number of case studies, and I've shown you some well controls on earthquakes. We have an understanding of what physically is occurring in the area. So let's try and do something with this. Let's try to understand, maybe make some forecasts of what we actually think is happening. And so the USGS has actually been doing that for the last 3 years. Here are images of the last 3 reports we were issued for 2016, 2017, and 2018, forecasting the earthquake hazard for 1 year. Now, this is really in the same tradition that we do earthquake hazard forecasts for natural earthquakes. I'm sure you've all seen the hazard forecasts for California, and those are going to be based in a 50-year perspective as opposed to a 1-year perspective. And the reason is, for these induced earthquakes, things are changing so dramatically, and it's not dependent upon tectonics, it's dependent upon primarily economic decisions. Things can move very quickly. And these are actually used pretty widely by regulators, insurance companies, and a number of people that operate a lot of infrastructure like dams, so that'd be the Army Corps of Engineers, state departments of transportation, the Bureau of Reclamation, things like that. And you can see this is just a map showing you the areas with highest chance of damage and associated with these induced earthquakes. Now, I should point out an important thing to note about this is right now we're just using statistical methods. We're predicting next year's earthquakes based on this year's earthquakes. We're not using any physics. This is what we're doing so far, but I'll show you some work that really is in progress to try to do a better job of this. And so we can look at what the hazard looks like with induced earthquakes and without induced earthquakes. And so on the right, you can see without induced earthquakes, the hazard in the central United States is pretty low. But if you include induced earthquakes, you can see there's a lot of hazard here in Oklahoma, and parts in Texas, and the Raton Basin as well. But, well, you'll say to me, Justin, well, come on. You just told me you know something about the physics. You know something. Why can't you do better? Well, we can. We know that injection is controlling seismicity. We know how close you are to basement is important, and we know the injection rate is important. And you can clearly see this. We're just looking at a number of different regions in Oklahoma. Shown in blue is the fluid injection rate. Shown in black is the seismicity. And you can see that there's a pretty reasonable correlation between the two. We also know the fault geometry. We've got this beautiful fault map of Oklahoma. So why can't we do better than a statistical model? Well, part of the reason is we don't really know the fault geometry. Now, all of these dots are showing you locations of earthquakes that have occurred in Oklahoma, and all of these lines are showing you locations of the faults that were in that fault map. Almost none of these earthquakes are happening on those faults. So we don't actually know where these faults are, so we can't actually predict the likelihood of earthquakes happening. We can predict the likelihood of these earthquakes happening on these faults, but all these faults appear to be more or less dead. And so we really need to start thinking about these newly observed faults where the earthquakes are occurring. So we don't know the fault geometry, so we can't really do a real probabilistic sort of experiment looking at the faults that we know about. So we're going to have to do something simple. But we still know a lot here. We know about the geology. This is a picture of what the basement looks like in southern Oklahoma. It's been exhumed. We also have very fine core samples, actually from depth, of both the Arbuckle, which is the injection formation, as well as the basement. So this is where the earthquakes are occurring. So we know something about the geology. And remember, we know about the injection history. We have data on the injection in all of these locations. So I apologize now for showing an equation. I do my best not to use them myself. But basically, what we're looking at the bottom here are 3 properties of the formation. So these are basic geologic parameters that we know. And then we take the injection rate. So we, again, have all of that information. And so then we're able to get our fluid pressures and the change in the fluid pressures. And from that, we're able to forecast our earthquake rates. And so let's go ahead and do that. And so what we're looking at here is the saltwater injection rate shown in blue. And shown, these blue spikes are the observed seismicity rate. And shown in red is our earthquake rate forecast. So I'd say we're doing pretty darn good. We're matching more or less the onset of the seismicity. We're predicting things to start ramping up in 2009, and that's really when we started seeing seismicity in Oklahoma. We match the peak of the seismicity in that we're getting it, the peak of the seismicity more or less right when it's occurring here, and we also are matching the decline. So not only are we matching sort of the general behavior, I would say that we're matching the amplitude relatively well. So this is really, I think, doing remarkably well. I'm using a 4-parameter equation to predict the behavior of seismicity, and it's working really, really well. And while this is a very broad perspective, we can do this on a much narrower scale as well. And so here we've made forecasts of seismicity for 2013, 14, 15, and 16. And the shading is going to be showing you the predicted earthquake rate, and the dots are going to be showing you where the earthquakes actually happened. The obvious takeaways here are, well, nearly all the earthquakes are happening in the green areas, and you're seeing more earthquakes in the areas that have the darkest green. So we're doing a pretty good job. So we've now developed a model that we're going to start pushing forward to make these hazard forecasts. But, well, there's a new wrinkle, and that's the scoop and the stack plays. So most of the oil and gas development that we've been seeing associated with earthquakes has been in this area and this area. And so these are the Hunton Formation and the Mississippian Formation. These are two different plays. And so you can see there's a whole lot of earthquakes in this area, but development is starting in this blue outlined area, the scoop and the stack plays. And you can see there's not a lot of earthquakes here. Those are the dots. And in 2017, you see a few more. And so this is really representing a challenge for us because it's really hard to forecast seismicity where you haven't seen seismicity. And there's not a whole lot of wastewater disposal in this area. And what we're actually realizing is that most of the earthquakes in this scoop and stack area are actually caused by hydraulic fracturing. So here we're looking at a count of earthquakes per week in the scoop and the stack area. And you can see that there's these really short bursts of seismicity. And if you go and look and say, hey, when are they hydraulically fracturing? Well, look, it lines up pretty much perfectly. So what we've learned from this is hydraulic fracturing-induced seismicity is more common than we've thought. And really the only reason that we're able to see it in the scoop and the stack is because there's not a lot of wastewater disposal in the area. While the areas here in the Mississippi and in the Hunton have a whole lot of wastewater disposal, there's very, very little in the scoop and the stack. And so you're able to see the frac-induced seismicity, whereas frac-induced seismicity is going to be masked by this much larger signal. In general, based on these studies by Rob Skumo, who's a postdoc working with us here, we expect about 1% to 4% of the seismicity we're seeing in Oklahoma is related to hydraulic fracturing, and the rest is really related to wastewater disposal. Now, I've sat and talked to you here in California about earthquakes in Oklahoma. Well, let me bring it back home for just a minute. Don't feel sad. We have our own induced earthquakes here. In fact, we've got just about every kind of induced seismicity you could imagine. We have reservoir-induced seismicity. We have wastewater disposal-induced seismicity. We have the first hydraulic fracturing-induced earthquakes ever observed. So we've got just about every kind. But it's a lot more difficult to identify here. Just like I was talking about in Oklahoma, where you have this high seismicity rate due to wastewater disposal, here we have a high natural seismicity rate. So it's very hard to disentangle a natural seismicity rate that's very high from a low rate of seismicity that's induced. So let's wrap up starting to think about what is our future? Where do we go from here? Well, in Oklahoma, the earthquake rate is declining. It's declined 70% from 2015 to 2017, and 2018 looks like we're going down further. Great news. This is following reductions in fluid injection, which more or less makes sense. But this is due to two different factors. One is economics. The price of oil dropped from about $100 a barrel to about $40 a barrel at the end of 2014. So for industry, it didn't make much sense to be really heavily going after these areas when there wasn't a lot of profit to be made. There also have been regulations phased in by a number of regulators in both Kansas and Oklahoma, and we think that has also had an effect on the seismicity rate. but there definitely is a question. The price of oil is starting to increase. What is going to happen? But even though the earthquake rate is declining, we saw 3 of our 4 largest earthquakes to occur in Oklahoma occur in 2016 when the seismicity rate was already dropping. And this includes the largest historic earthquake to occur in Oklahoma, as well as the most damaging earthquake to occur in Oklahoma. And still, at the end of the day, yes, great, the earthquake rate is dropping. But we had about 400 earthquakes in Oklahoma, magnitude 3 earthquakes in Oklahoma last year. That's still 200 times the background rate of earthquakes. So I don't think the people in Oklahoma are really happy with that still. But it's not all doom and gloom. I think these gentlemen with John Bredehoft really showed us that we can control induced earthquakes to some degree by affecting the fluid pressures that we're looking at. And there have been regulatory successes in a number of different locations, in Greeley, Youngstown, and Love County. But we've also learned that distant earthquakes can't be stopped instantaneously. There's an area called Paradox Valley in southern Colorado where we're seeing earthquakes over 10 or 15 miles away from the injection. So if you suddenly stop the injection, the earthquakes 10 or 15 miles away are not going to hear of that for years. And some sequences also continue long after injection stopped. I showed you a Rocky Mountain Arsenal where we had the largest earthquake a year after injection stopped. We're seeing earthquakes there 15 years after injection stopped. So these can be very long-lived sequences. States are taking action. 7 different states have enacted regulations to respond to induced seismicity. And the EPA, who sort of oversees all the regulations on injection wells, has released guidance on minimizing induced earthquakes. The USGS, we're now issuing hazard forecasts, right now based on these statistical models, but we're pushing forward to take these earthquake rate forecasts all the way to hazard with these models that are based on physics. We've moved past just these simple statistical models. And I shouldn't just toot our horn. There's some very nice work done by colleagues over at Stanford where they're also using physics to forecast these induced earthquake rates. So moving forward, our high earthquake rates are continuing. They are declining, but it appears perhaps that they can be managed to some degree. And we haven't seen any really large earthquakes yet, and we really can't count those out from happening. But one thing that we need to think about is earthquakes in the central U.S. are potentially more dangerous than earthquakes here. People are not building to the same construction standards in Oklahoma as they are here. There are no earthquake engineering regulations in Oklahoma like there are here, and so buildings are going to be more susceptible to strong shaking there than they are here. Things looking up, our ability to make forecasts is improving. We're finally starting to integrate some of the physics that we know is going on to make these earthquake rate forecasts. And where there's been a lot of incredible collaboration and cooperation between regulators, between academic scientists and industry. And I know that's a little bit remarkable. I was impressed when I started working with industry. But at the end of the day, industry, this isn't good for them. They want to stop the earthquakes as well. But I'm a scientist. I think we've made a lot of great progress in this, but more research is needed. I think there's both a great societal benefit here in that our research can really help reduce these earthquakes, but also there's a lot to learn about earthquakes in general, both induced and natural, by studying these earthquakes. So last, I'll just leave you with a couple places you can get more information. On the left-hand side is a picture of a handout that I've got in the back that is a plain English discussion of induced seismicity. So if you forgot something that I said, didn't get something that I said, that should cover it. And we also have a website there with more information about induced earthquakes. I'll end it here and be happy to answer any questions.
Thank you, Justin. I'm going to remind people with questions to please step up to the microphone so our online viewers can hear you.
Hello. This is a technique question, I guess. You mentioned a lot of those models based on points of local stress in the ground. Can you talk a little bit about how you measure that? And, is that getting easier to measure? Is that getting harder to, I don't know. What are the instruments used for that?
Okay, so we actually don't have a whole lot of measurements of stress at depth. That's very, very difficult. There are stress sensors that are buried in boreholes, but in general, those are incredibly expensive and not always all that reliable. most of what we're doing here is really stress that's being computed from numerical models. We're taking what we know about the Earth and taking what we know about the injection and predicting what the stresses are. Now, there are a handful of monitoring wells. And so the USGS, we run one. The Oklahoma Geological Survey, I believe, has about a dozen, where they actually they've managed to convince an operator to let them take over one of their disposal wells. And they've basically dropped a float into that well. And as that float goes up and down, we know what the fluid pressure is. And so that is incredibly valuable information, because otherwise we have no way of knowing what the fluid pressures are in this region. And so we're learning a lot about what's happening. The data is slowly starting to come out, but I think it's really exciting, and I think we're going to learn a lot more from it.
I have heard that there are some climate change deniers, and I'm wondering if there are also induced earthquake deniers, or if this is generally accepted science.
Well, I think within the scientific community, it's not under debate. Certainly, I've run into people that want to sit and argue with me, but I think the number of those people really is declining over the years. I think, I've been going to scientific conferences on this for 7 years now, and 6-7 years ago, industry wouldn't deny that Rocky Mountain arsenal was induced, but they deny that oil and gas induced earthquakes existed. And a few years later, they're like, well, maybe. And now that they'll admit that there are earthquakes that are induced. They won't admit that they're inducing earthquakes. Actually, a few operators are now starting to admit that. So there's a progression here. And like I said, I've actually been really impressed in general by industry, and that at the end of the day, they want to fix the problem too. So it really hasn't been a hostile working relationship. In general, it's collaborative.
Continuing on that, have you ever faced any resistance from companies in terms of the research you did at all, especially the Rangeley experiment? That sounded like it was especially collaborative. So, are there instances that you can think of where they weren't collaborative? And question 2, it may sound like a stupid question, but when you extract oil out of the well and you said there's salt water coming out as well, can you not just put that salt water back after you're done with the extraction?
Okay, both good questions. Like I said, in general, our relationship with industry has been pretty collaborative. Sometimes they give us data, sometimes they don't, and in fact, a lot of the time they don't, and that in general has to do with their lawyers as opposed to their scientists. And I primarily work with their scientists, as you would expect. Certainly there are scientists from some oil and gas companies that walk straight past me at meetings, and that just sort of is what it is. But I think I've had maybe one hostile interaction ever with an oil and gas representative, and he and I had known each other for years, and it was basically there was a press release that his bosses didn't know about, and they came after him, and the next day everything was fine. So in general, it's been really positive. With Rangeley, that was remarkable. That was 50 years ago, and I don't know if Barry, Jack, and John were just incredibly charismatic men that convinced Chevron to give them control of their field, or I think business was done a little bit differently. People weren't as concerned about liability at the time. Your second question, just remind me again. I'm sorry.
Can you put the salt water?
Oh, can you re-inject the salt water? That's a great question. And so that is actually more or less what's called enhanced oil recovery, where you put water down into the same formation. You can do that, but in general, it's not being done in these locations. And the reason it's not being done in Oklahoma is they're extracting these out of what are known as generally tight formations. These are formations that aren't very porous, that aren't going to accept fluid very readily. And also, you have this problem that you have very little oil and lots of water. So if you're putting more water in there, you're going to be in some sense diluting your supply. And so you really want to get the salt water out. That obviously would be a preferable solution. But as I showed at the beginning of the talk, enhanced oil recovery can cause earthquakes, but in general we wouldn't expect it to, because there's going to be a fluid mass balance and a fluid pressure balance. But doesn't totally work, and in this location it just doesn't work.
Okay. I've got two questions as well. First, on about 4 or 5 slides back, there's one where you showed a temporal chart at the bottom of the wastewater injection correlated with seismic activity, and you overlaid it on and showed that there was a 1-to-1 correlation.
Yeah.
My question is...
So like this?
No, a little bit further. There were individual stripes of red.
Oh, hydraulic fracturing. Sure.
Yeah, there you go, yeah. The implication is that each one of these things is very punctuated, where there's almost no activity, and then a whole lot. That seems strange. Can you explain that a little bit?
That's a great question. So we think because hydraulic fracturing is such a short-term process, and it's a very high-pressure blast, but it's a low amount of water that's going in. So we expect the pressure blast to drop off really dramatically. And so that's really what's happening here. You're not affecting a very large region. You've just blasted it really hard. You have earthquakes during that quick blast, and then it more or less goes away. In general, most frac-induced earthquakes are within 2 or 3 days of the frac job. I've seen earthquakes 30 days after, but that's incredibly rare.
Good. Okay, second question. On the map of the U.S., you mentioned that this Scoop and Stack area and the places in Oklahoma have a very low background of natural seismicity. The place, however, which does not have a low background is the New Madrid Fault in southern Illinois.
That's right.
The injection, and that sort of adds a joker to the background of this natural stuff, and that frankly scares the bejesus out of me after what happened in the 1800s there.
There isn't a whole lot of oil and gas exploration right on the New Madrid seismic zone. There is some in southern Illinois and southern Indiana, but we're not seeing any seismicity associated with it. But yeah.
So far.
So far, yeah.
This question is partially political, so you may have difficulties with it. But because of the fact that the liability could gradually build up, and therefore there could be a lot of lawsuits against the oil fracking companies when you saw the earthquake damage to some houses, first thing you do is get a lawyer and sue the company. Has you seen that happening? And if so, has the Trump administration starting to clamp down on your research?
There are ongoing lawsuits in a number of different locations where oil and gas companies are being sued, either in class action suits or by individual people. To my knowledge, none of these have been resolved. So far, nobody upstairs has been complaining about my research.
Good.
So, and I hope it stays that way.
So I think I heard you talk about pressure and stress. I don't remember hearing much about energy. So if you compute the energy you put in, does it equal the earthquake energy?
No. The amount of energy, basically, so the amount of mass times the change in elevation is much, much lower than the amount of energy that's released in these earthquakes, or many orders of magnitude.
So just the intrinsic stress in the rock itself that you
release.
release?
Stress within the earth that's being released, yeah.
Okay. And the other question is if you can induce earthquake by injecting water. I heard that tides don't create earthquakes. So why is that? It's just the magnitude of the pressure involved?
So people have been looking for tides causing earthquakes for decades. Actually, there's some studies going back to the 1800s. And people see connections in the most extreme cases where you have these massive tides, but in general you don't. And there's a big part of it is just the pressure changes are so low. And that's the big source of why we're not seeing it.
Okay, thanks.
Hi, first, thank you for your presentation. It was very good. Speaking about delayed and spatially removed events, after injection stops or far away from injection, I'm just curious what the travel time through the rocks are. I'm sure it varies with all kinds of stuff, but I'm sure there's fluid transport, but there's also pressure waves, which wouldn't necessarily mean the fluid's moving. So I'm just curious. Can you just put some numbers on how fast these things are moving through the rock at all, or not really?
It's pretty hard. It's primarily going to be dependent on your permeability. So that's a characteristic of your rock. And there's going to be sort of a general permeability of the rock, but also these rocks are going to be fractured. And so the fluid pressure can transfer much more quickly in the fractures. And so if you have a long fracture, it's going to travel much more quickly. And an important thing to remember is that it's not that the water actually has to get there, it's just that the fluid pressure has to get there. So if you think about like your hydraulic brakes, it's not like the brake fluid that you're stepping directly on is going all the way to your brakes. It's just that pressure that's being transferred.
Right, but there's still a pressure transmission rate,
yeah,
right?
Well, so it would be hard for me to put a number on how quickly it's going to move, but relatively quickly. I mean, you can move a kilometer in a month, no problem. But you also need to consider, if you recall, I talked about two mechanisms. I said fluid pressure is the bigger source of it, but also those solid stresses are important. And so the recent studies that have been looking at poroelastic stresses, so solid stresses, those stress changes are almost instantly transferred. And so it's a tough game to try to figure out. I mean, that's one way we're able to figure out that poroelastic stresses are important, is these stresses are getting there too fast for it to be a fluid pressure based thing.
Thanks.
We live in Monterey County where fracking and other oil-related issues are very hot, including we've got an election where Chevron is pumping hundreds of thousands of dollars against a very good anti-fracking candidate. What can you tell us about our area, about what we should be watching for, things like that?
It's a good question. So, the Monterey Shale has been known about for probably a century or so, and a number of years ago, people were really we're saying it was the next Oklahoma or the next Texas, and we've more or less figured out that that resource is much smaller than we originally thought. I think it's about 4% of the size of what was originally thought. Sort of what can be done there is what can be done in Oklahoma. It's just enhanced earthquake monitoring. Obviously, we've already got a good monitoring network, and so looking for connections between the timing of frac jobs and the timing of earthquakes is sort of the obvious first step.
Thank you.
Yeah, two questions. A quick one is, what sort of pressures are you talking about when you're pumping this stuff back into the ground? And then the second one, though, is more, they haven't mentioned anything about offshore, and if there's anything in marine oil deposits and stuff, if this comes into anything in those areas.
Okay, so sorry, the first question was?
Just how much pressure?
How much pressure? So actually a lot of these wells, they're actually not injecting under pressure, they're pouring the water down the well. And so it's literally just the weight of the water that's increasing the pressure. So you're looking in some of the lower areas, you're looking at tens of kilopascals, but with the monitoring, the pore pressure monitoring that we have, we've seen a rise of nearly, I believe, a megapascal over the course of a year. So a lot. It can be very high. As far as offshore, truthfully, I'm not particularly knowledgeable about what is really happening out there. I mean, those are, in general, what's happening offshore are older reservoirs, areas that have been exploited for a long time, and so those are going to be areas that are going to be high cut. So they're areas where there's a lot of oil and not a lot of salt water. So if that is the case continuing forward, I wouldn't expect there to be a high probability of earthquakes, but it's really going to be dependent on what the activities are now.
There's no actually pumping and recharging back in offshore.
I don't know what the operations are offshore.
I have two questions. One on behalf of my wife, who was too shy to come up here and ask it. The water that's being injected, is it clear, clean water, or does it contain chemicals, and does it have any effect on drinking water?
In general, the water is pretty nasty, and that's why they have to inject it at depth. And now, the water is nasty not because of any oil and gas operations, it's because it's nasty to begin with. It's usually 100,000 parts per million dissolved solids, so that's pretty much salt. So that's 3 or 4 times saltier than the ocean. So it's really bad stuff. And there's also going to be things that are going to be leached out. There's often arsenic and things like that in there. And so, but in some areas, the water that comes out is actually very clean, and either very minimal amount of effort needs to be cleaned. Needs to be taken to clean it, or even sometimes no effort. But in Oklahoma, it's generally incredibly salty.
But does it have any effect on drinking water?
No, so they're injecting these into in general, very deep wells, far below the drinking water aquifer.
Okay. And my other question, I wanted to take you back to one of your earliest slides. You don't have to go there, but it was the picture of the Joker and threatening to, I think it was dumping seawater into the San Andreas Fault. Was that it? Or
yeah, it's Lex Luthor trying to put water into the San
Andreas Fault.
Yes.
And it just put in my mind, you know, we're constantly hearing in the Bay Area about the threat of the big one coming and, you know, all of these percentages and so forth, and we all sort of expect it eventually. And earthquakes, as I understand them, are due to the relief of stress, and the stress is constantly building up. Could there be any beneficial application of this to reduce this stress so that we had a whole bunch of smaller earthquakes rather than the big one?
If only that was the case. Well, there's a couple of different problems. One is that, well, like we've seen in Oklahoma, they can't control how big these earthquakes are, and so we wouldn't be able to control how big the earthquakes are in Oklahoma, and so, or here in California. So, you know, what's going to happen is Earth is under control. We're not under control. And the other problem, it's an energy problem. So each magnitude that you increase, each increment of magnitude you increase, the amount of energy increases by 30 times. So to release the amount of energy that's released in a 7, you need 30 magnitude 6s, or give or take 1,000 magnitude 5s. Or let's say we want 3s. Those probably aren't going to cause damage. You'd need 1,000,000 magnitude 3s. And at that point, I might just take the magnitude 7 and move on with my life. So it just doesn't work from an energy budget perspective either. But yeah. If I was able to do that, I'd be a rich man. But.
Yeah. That town where all the pipelines converge. Cushing. I would hope people are looking at that.
Oh, of course, yeah. So we've got a lot of monitoring in the area. The operators in the area take this very seriously. They're running their own seismic networks to monitor what's happening, and they have very specific procedures in how to respond if there's a certain amount of shaking, and it's generally very low, and so they have to inspect every single tank. And obviously, they've got a lot of procedures in case to respond in case of a failure of one of these, because it would be pretty catastrophic if one of them failed, much less a number of them fail.
One more quick question. This is about general in wastewater. I know that during the operation of wells, there's a whole lot of wastewater that can come out for the whole life of the well, basically. And it's a problem on land where you don't want to put it in the sewer system. My question is about offshore. Is it regulated in United States waters where they just can't dump that stuff straight back in the ocean? And the same question about overseas, foreign places.
I'm going to say I don't know to both questions. As far as injection on land, that's controlled by the Safe Drinking Water Act, and so that's where the regulatory authority comes from. I'm sure there's some amount of regulations as far as offshore. Internationally, what is done, it's really highly variable. I've worked with colleagues in Italy and colleagues in Colombia on similar issues, and everybody has their own sets of regulations. But yeah, it's really highly variable, and in general, the regulations for this sort of thing weren't made for earthquakes. They were made for keeping water clean, and so people are just sort of figuring out how to deal with it as it comes. So I don't think anybody really, any country at least, has a real organized way that they're responding to things.
Going back to your equation that you showed, can you tell us how the stress or the pressure induced earthquake related to the magnitude of the earthquake? And also in Middle East, they are doing all these oil productions. Have they seen any kind of these kind of induced earthquakes as well?
So are you talking about this figure right here? Is that? Oh, the equation. Oh, so no, we're not forecasting the magnitude of these earthquakes. Basically, we're forecasting an earthquake rate. There are sort of traditional ways that we're able to take sort of a total earthquake rate and more or less back out the number of magnitude 4s that we'd expect and back out the number of magnitude 5s that we'd expect. And so those are the sorts of relations that we would use. As far as what's happening in the Middle East, I don't know a ton about what's happening there. So I'd be loath to really comment at length about it. I do know there are induced earthquakes there, but I don't know much more.
Okay, any more questions for Justin? Nope. Okay, well, I want to please remind you to do come back for our July 26th lecture on acid mine drainage, and please give Justin one last big round of applause. Great job, Justin. Thank you.